myself, never accept a speaking slot immediately following Frank 80. Bad idea. As mentioned, I'm Paul Gruen, Advanced Technology at Cray, and I neglected to put up here my other role as chair of the Open Fabrics Alliance. We have a really nice collaboration going on between the OFA and SNIA, mostly focused on remote persistent memory. There's been a lot of discussion about technology over the past number of years here at the PM Summit, the Flash Memory Summit, and the OFA workshop in the spring. A lot of discussion about the low-level details of the technology and the various form factors and so on. But a year or so ago, we started shifting the focus away from the technology and more towards how that technology is going to get used, thinking that that might cast some light on how the technology ought to develop and how you're going to apply the technology. So I gave a session, or it was a session, Rob just mentioned it, at the Flash Memory Summit in 2018, where we started to shift the focus away from the technology and more towards the use cases or the applications or the consumers of remote persistent memory or persistent memory in general. So I'd like to sort of revise and extend my remarks. A lot of what was being said at Flash Memory Summit is being amplified and sort of enhanced here today. So I think many of us view that slot, and Frank did a pretty good job here. There's that slot in the middle in the hierarchy, and we all tend to think of that, or many of us do, as kind of monolithic, and we're headed towards nirvana, and maybe Optane is nirvana, I don't know. But nirvana being defined as infinite capacity, infinite bandwidth, zero latency, and zero cost. That's where we're all headed. We'd love to be there. Oh yeah, and infinite retention as well. But the truth is that there's lots of trade-offs to be made. So I wanted to dig a little bit into those trade-offs today and try to understand how those are going to impact what we're going to do with persistent memory going forward. So here's my cartoonish version of Frank's very elegant pyramid. It's clear, I think, to all of us that persistent memory isn't exactly memory and it's not precisely stored. Somebody gave me a hard time about saying it's not exactly memory, because it has the word memory in it. In fact, it is memory, but it has that modifier persistence. So it's not exactly like memory, and it's not exactly like storage. So there's this gap in the middle, and I think we all know that. It's a bit of a dessert topping or a bit of a floor wax. Can't quite tell which. So what do we do with this, and how are we going to use it going forward? I submit that one thing we could do is dig into that little gap in the middle, this new tier in the memory hierarchy, and think about it in a little bit more detail. And I'm suggesting that the first thing we do is partition it into local versions of persistent memory and remote versions of persistent memory. And within each of those tiers, there's various trade-offs to be made as well, even within those sublayers. This really isn't, I don't think, that surprising, but I think it's worth thinking about, the differences between performance devices, capacity devices, and are you going to use this thing locally or remotely? So that leaves us with a bunch of choices. How you're going to select the right technology that you're going to use, I'm going to resist the joke about Optane here, is really going to depend on a couple of things. One being the system objectives. What are you trying to accomplish with your system? What's the purpose of the system that you're building? And similarly, what are the application requirements that you're going to run on that system? Those are going to drive us towards particular choices, I think, in various technologies and how you're going to deploy it. So resolving these trade-offs among persistent memory solutions, the available solutions, assuming that we don't actually hit nirvana, which we probably won't, it depends on system objectives and the application requirements. So that's what I'd like to dig into a little bit today. So we're going up the stack here, and we're talking more about how you're going to apply persistent memory from the consumer or the application perspective, and that's going to drive the technology discussion below us, as opposed to what we've been doing so far, which is talking mostly about the technology and then wondering how we're going to fit applications on top of that. So a couple of likely targets for persistent memory. Those who read this slide will find all kinds of problems with it, so we could use some help here to really clean this one up, because I'm not an expert in any of these areas, but things that I hear mentioned frequently are things like database applications. SAP HANA was mentioned. And there's really two really uses of that, where I've got one sort of described under database applications and the other under graph analytics. But in both cases, you can consider either a larger in-memory database, so you can support a larger database application, or a distributed database. That becomes a possibility as well. Data analytics, you want to be able to create this database just once, and it's in persistent memory. You can run multiple queries against that database without having to reconstruct it each time. Same thing is true with graph analytics. If rather than having to spawn the graph each time, you could just simply spawn the graph once and leave it in persistent memory and then re-access it over and over and over again, there's some advantages to be had there. Craig's been messing around with that a little bit. Commercial applications, this is one that we've heard discussed a couple of times. The best example was given by our friend from DreamWorks, Scotty Miller, who talked about collaboration on large-scale projects, where you had a whole bunch of animators all working on a movie, but each animator could only see a very teeny piece of the movie on his own local workstation. He couldn't see what anybody else was doing, and he was limited to working on, I think he said, 8 seconds of the movie. So if you could create this large capacity, remotely accessible depot, let's call it, maybe you could expand the team and the team could work more collaboratively and do a better job in animation. Scotty did a really nice description of this at the Flash Memory Summit. Go dig up the slides. He's a fun speaker and it's fun watching him talk about it. And last but not least, my favorite HPC applications. So for scalability purposes, parallel applications, things like that, there's obvious, I think, opportunities there for taking advantage of persistent memory. So just some likely targets, not inclusive by any means, not the end-all, be-all list, but just sort of give us an idea. So what are these system objectives that I've been haranguing about? Again, it's not an exhaustive list by any means, but a couple of them are data availability and protection. Doug Voigt and I were having a fun discussion last night about, is this really high availability, which is what we've called it up to now, or is it really about data protection? And kind of resist using the word protection because all of a sudden that means to people, that means data backup. And we're not talking about data backup. We're really talking more about, is data available when you need it and you don't lose it during a power cycle? Local system performance, what if you, and this is going to get a little dicey here, but what if you replace an access to a rotating media device with an access to a flash device where you didn't have to go through that hairy stack that Frank drew the picture of, and you could access the memory directly. So you can enhance system performance just by eliminating disk accesses because you're not going to disk anymore. Scale-out architectures, this one's pretty obvious, I think. Distributed databases, analytic applications, HPC applications, and so on. Scale-up architectures, this is where you're really just increasing the capacity inside a local server. Disaggregated system architectures, this is where you can potentially decouple the scaling of the compute with the scaling of the memory, such that you can scale them independently. If you have remote memory, you can scale that independent of the memory that's on a local platform, and maybe you have this new model where you have pools of compute and pools of memory, and you can scale them independently. Shared data, that's the one I just mentioned a moment ago, the DreamWorks example. And then improved uptime and fast restart. So, what happens if the server takes a power hit along the way? Can you bring it back more quickly? There's a whole bunch of these possible objectives. This is not an exhaustive list. It's just the ones that came out of my fertile imagination. The one that's crossed off at the bottom there is improved disk storage performance, because we're not talking here about replacing hard disk drives with SSDs. That's a topic for another conference, not the PM Summit. Okay, so some of the consumer considerations. What do we mean by consumer, first of all? The consumer is not the guy that's ordering from Amazon. The consumer is the person who's consuming, or the application that's consuming memory services. So I tend to use this word consumer quite a bit. When I say that, that's what I'm talking about. So there's a couple of objectives that an application might be trying to meet, or it might have a couple of requirements. For example, the first obvious one, is it performance or is it capacity? And that, I think, is pretty obvious. Are you looking for something that goes faster, or are you looking for something that goes faster in large quantities? It's not to say that these are diametrically opposed, but we do often find ourselves making that trade-off between performance and capacity. The sharing model, is the data between multiple processes being shared? Or is there a shared service versus a dedicated service? So is there a node out there somewhere that only you can use? Or is there a node that's being shared between amongst of other processes running on other nodes in a cluster kind of environment? There's some thinking there about what the memory model, the sharing model actually looks like. And that's going to impact the kind of building blocks that we're going to need to provide as an industry in order to make this stuff take off. Likewise, the memory model. Are we talking about traditional flat memory accesses where you're doing reads and writes to a memory region, or are we talking about an object store model, for example? Characteristic traffic patterns and traffic engineering requirements are going to factor into the choice of which technology is going to make sense. You're doing small byte operations, or are you doing large bulk data transfers, or some combination thereof? The answer, of course, is yes. There's ordering semantics, there's atomicity, and there's a bunch others. But just to give you a flavor for the kind of things that it's probably worth thinking about when you consider what your application looks like that's going to be taking advantage of this persistent memory technology as it emerges. So that leads us to this question about the trade-offs. And I tend to draw things in kind of black and white lines, so I've done that here. It's obviously not like that, but I think about it in terms of DRAM replacements. Then there's capacity devices at the bottom end, and then there's sort of gap fillers in the middle. And this is not hard and fast by any means. Just my point here is to make the point that there are these trade-offs to be made. Byte addressability versus block addressability. You could, in theory, build a byte addressable device by wrapping stuff around a block addressable device, but I'm not sure that's a good idea, but you could. There's other things to consider here, the form factors, NVDIMM-N, NVDIMM-P, PCIe. I don't want to go into any of this today because you've heard about these sort of endlessly. And lastly, the question of locality. Are you talking about local remote memory or local persistent memory or remote persistent memory? So a couple of trade-offs that need to be considered here. All right, now, here's the sort of the point. Not all applications actually value persistence. I think sometimes we kind of get caught up in the idea about it's all about persistence. Frank did a really good job of disabusing us of a lot of that by pointing out that there are really performance and capacity trade-offs to be made. But persistence might be valuable in some applications. For example, high availability applications where you really can't afford to lose data between power losses. That's one good example. Reducing or eliminating the need to access slower media like hard disk drives. I referred to that before. If you're doing memory operations to a memory device that's known to be persistent, all of a sudden you don't have to do a block read or write to a storage device, and the application will run faster. Data protection and preservation is another one. This is a favorite of mine. This is the high availability case that we talked about before, where when the server suffers a power cycle, you want to know for sure that the data that you are working with is still there. For example, the database that you spent a lot of time building didn't go away. It would be nice if it was still available. In some cases, persistence is required, but not required, but nice to have. These are applications that tend to focus more on capacity and or performance. So analytics, for example, requires establishing a database. So you build that database just one time, and then you'll be able to run multiple queries on top of it. It's really about the capacity in that case. It's not so much about persistence, but persistence is a nice capacity and a nice characteristic to have. So in the cases where the application doesn't actually need persistence, the so-called convergence of storage and memory becomes sort of uninteresting, and you look at it more as a capacity versus performance trade-off. So in my mind anyway, since I'm a network guy and think about networks all the time, the first order trade-off that we should be talking about is local versus remote. And again, this would be in a cluster kind of environment or a mainframe sort of environment. There are some requirements that are really met by just citing a whole bunch of persistent memory on the local compute node itself, just expanding the capacity available on the local compute node. So capacity-based applications, I talked about scale-up databases, for example, or in-memory databases being able to support larger ones. Some high availability uses in the cases where you're not worried about the loss of the compute node, but you are worried about the data between power cycles. That could take advantage of local persistent memory. Likewise, replacement of local storage for performance reasons. I harped on that a few minutes ago, so I won't spend more time there. But for others, it's really all about distributing persistent memory throughout the system. So in this case, the good examples here are this idea of the disaggregation of compute and memory, or the ability to disassociate those two such you can have independent scaling of compute and independent scaling of memory. That's a sort of an attractive but emerging model that has a ways to go until we get there, but it could be taking us in that direction. Shared resources or shared data, so the team collaboration model I talked about a minute ago, where you have a bunch of animators all working on one large movie, and that movie is in a shared database somewhere on a fabric that can be reached. That's the team collaboration model that I mentioned. So there's a first order trade-off we probably ought to think about, local versus remote. So the local case, let's talk about those for just a minute. What are some of these use cases? And I had listed before 1, 2, 3, 4, 5, 6, 7, 8 or so use cases way in the beginning. Some of those are more applicable to the local persistent memory case, and those are the ones that are kind of outlined here. So local system performance, the scale-up architecture, and improved uptime and fast restart are the ones that I listed that seem to lend themselves more naturally to just expanding or placing local memory, persistent memory, on a local compute node. And there's trade-offs to be made here. So if your objective is performance, you're probably, why did I say persistence has 3 check marks? That makes no sense. See, you were reading that. You picked that up. Thank you. The point here isn't whether, to debate how many check marks are in a given box. The point is that you really ought to be thinking about what is it that your application really requires in the 3 use cases that I'm talking about here in this particular case, performance versus scale up versus fast restart. And again, those were just examples. I just want us to start thinking about what are your system objectives and what are the application requirements, and let that drive your choices. Shifting to remote persistent memory, just to set the groundwork here, this is the model that I tend to keep in mind when I think about remote persistent memory. It's a persistent memory service that resides on a fabric somewhere and is accessible from a number of processes, also distributed on the fabric somewhere, whether it's a cluster or some other architecture. And the memory that is provided by those persistent memory nodes, those target devices, if you will, it could be shared or it could be unshared. So you could have a number of processes all sharing that region of memory, or maybe a region is allocated to each process. So that's kind of the model that I keep in mind. So shifting onto the use cases for remote persistent memory, data availability and protection is the one that comes to mind most frequently. This is the one where I've been trained to say that if data isn't in 2 places, it's really nowhere. So this is the high availability use case that SNE has been spending a great deal of time working on the past couple of years. Scale-out architectures, this is a favorite of mine working for Cray. We do this kind of thing a lot, distributed applications, parallel applications running in a distributed environment. Disaggregated system architectures, again, a bit of a pipe dream, but I think a direction we may actually be going, depending on how fast persistent memory devices become. And improved uptime and fast restart. Let me talk for just a minute about the 3 key ones. The data protection use case. This is a picture that was shown at Flash Memory Summit. The next 3 are just like this. That just sort of illustrates what I mean. And in this case, we're talking about data that's written to local persistent memory and mirrored to remote persistent memory, more or less simultaneously, such that data is in 2 places at the same time. The scale-out use case, this is where there's memory available on a remote node, and regions of memory allocated to different processes running on different nodes, so there's no real sharing of data going on here. It's just more about expanding the available capacity, but doing it externally, not internally, not through local persistent memory. And finally, the shared data use case, this is the one where the persistent memory is actually shared amongst processes running on different compute nodes. And all 3 of these have implications on how the network actually functions, how the application actually accesses that data, what kind of management structures are going to be required, and so on. So I just kind of wanted to point those out as things that we ought to think about when we're talking about developing remote persistent memory in this case. And in the same chart, and again, you could quibble with me about the check marks. I probably have them all wrong, but draw your own check marks and in the way that you see fit as your understanding of the application that you're trying to service sees appropriate. All right, a few interesting applications for remote persistent memory. High availability is an obvious one. HPC checkpoint or restart. This is a problem that we in the HPC world grapple with all the time. You want to make your systems available or highly available, so you checkpoint them on a periodic basis, and you get to the point where it takes longer to checkpoint than it does to do any actual computation, so you actually make backwards progress. So you can improve checkpoint restarting by using remote persistent memory methods to do that. Again, these are not remote storage devices. This is remote persistent memory. Distributed collaboration, I've harped on this one quite a few times. Machine learning was mentioned, sensor data ingest and analysis. This is one where data comes into the system and is put into persistent memory, made available for analysis by a distributed team. By the way, most of these came out as the result of a think tank that we held at the Open Fabrics Alliance workshop last year, and they're going to form the basis of a paper that we're developing collaboratively with SNIA to describe these use cases in a little bit more detail, which we hope will help drive the industry in the same way that the high availability white paper is driving our thinking about high availability and persistent memory. And finally, I'm almost done here. I think I'm right on time. A couple of challenges with remote persistent memory. By definition, it's NUMA. So if you have an application that absolutely depends on symmetric accesses, well, you need to go somewhere else because this isn't going to work for you. By definition, at least today, until we get to infinitely fast and infinitely low latency and so on, it's always going to be a NUMA environment. Don't think it's a big problem, just something to think about. Therefore, it's going to generally require, in the case of remote persistent memory, it's going to generally require asynchronous operation. You can't make the speed of light disappear to the point that you can do synchronous operations like you can with remote memory, with local persistent memory. So ultimately, remote persistent memory is almost always going to wind up being an asynchronous operation. And that's because networks introduce unavoidable latencies, which are okay as long as the application can tolerate it. Not all can, maybe many can. And the transaction model will often favor pull versus push operations. So, you know, we're used to thinking in local memory, you do a write to memory, a write to memory, a write to memory. In the remote persistent memory case, it's often the case that you use kind of a storage model where you send a request to the remote target node and it winds up doing the pull across. So there's a little bit difference in the transaction model. The point I'm trying to make here is that you probably can't treat remote persistent memory exactly as the same as you would treat local persistent memory, although that is the objective, but you can get pretty close to it. Okay, last slide, Pithy Commentary. I suggest you understand the use cases first. That's what this is all about. So understand what your system objectives are, understand what the characteristics of the applications you're trying to support are, or the applications you would like to see emerge in the near future. Understand those first. Consider all the attributes of persistent memory beyond persistence. So think about capacity, think about performance, you know, think about local versus remote, all those kinds of things. And there's others as well. And then consider the chicken and the egg. You know, in some cases, you can simply substitute persistent memory for, you know, DRAM, and by golly, you get an application that runs faster. That's great when that happens. It doesn't happen too often. In some cases, we're going to find that persistent memory turns out to be an enabler for new application models. Think about that one, too. Don't just think about the existing application models. Think about what you could do with it if you had it. And that's all I can think of to say. I think I'm right on time.
Thank you, Paul. We do have 3 minutes for some Q&A for this very good speaker. So in the back.
Paul, one issue with persistent memory that I hear mentioned very infrequently that
Just
I think
one?
is kind of, well, yeah. I mean, one I'm particularly focused on anyway, which is in this modern world, whether it's our desktop PC or a node in a cluster, when something hangs or we get a crash or whatever, we just reboot it. And of course, in this world, if the state is exactly the way it was at the instant where it crashed, you get the same result. So this has got, I think, implications on software and OS. Can you comment on that?
It certainly does. Not to be flip, but I think, you know, we understand that phenomena. There's this question about what high availability actually means. Do you have to roll back in time to find a snapshot that works? You know, And really the point here is narrowing the window between the time when you did your last snapshot and your current snapshot. If you have to roll out to a checkpoint, that's one thing. If you just have to restart the machine to its current state, that's another thing altogether. It happens a lot faster. But that's an interesting and thorny question. I don't think there's a good answer for it yet. We need to work on that.
One more question?
Yep, time for one more. Anybody? Going once? All
Going
right.
gone.
Quick comment. We
I'll
got
just
it.
jump up and make a comment. This is Tom Talpe. The question of error recovery is of high interest to the SNIA non-volatile memory programming twig. We've been working on it for a couple of years. It's in our current draft version of the white paper, and there's quite a bit of thought going into that matter.
Very
Hence,
good.
not a solved problem, but a problem being worked.
That's exactly right. Let's give the speaker another hand, please. Thank you.